Now we will see a simplified fatigue calculation. This is the vessel for which we will make the calculation. By the way, this vessel was already used as a sample vessel for a technical report, a CEN technical report made many years ago, just to give an example of application, of practical application of the new rules. This report was made in accordance with the edition 2009, so the very old edition of the standard, which has been now greatly modified. We will calculate the fatigue resistance of this vessel according to the actual rules, that is, according to the EN 13445-3, clause 17, issue of the standard 2021. We start looking at the item properties. This is the name of the vessel. This is the standard with the correct edition. The units are megapascal and degrees centigrade. The set of material is practically carbon steel, carbon manganese, silicium. Geometry is a vertical item. Tests, the test is a hydrostatic test. The test pressure is automatically calculated. The vessel is not tested in horizontal position. The test pressure is the test pressure which depends on the height of the vessel, which, by the way, is not very high. Location, wind, seism, loads, lifting, not interesting in our case, but fatigue, of course, is interesting. Number of load conditions, there is only one condition of fluctuation, which is, by the way, pressure-only fluctuation. Pressure range, the pressure range is 17.5 bar, 1.75 megapascal. Why? Why the design pressure, we will see this in operating condition, is 20 bar. Of course, the fluctuation cannot be from 0 to the design pressure, it will be to 0 to the operating pressure. Minimum and maximum temperature during the cycle are 20 and 260 degrees. Required number of cycles is 1200. Well, lining reporting option not interesting. Look at the operating conditions. Design temperature 260, internal pressure 20 bar, external pressure design temperature, we have no external pressure in our case, joint efficiency 0.85, external corrosion allowance, there is no external corrosion allowance, there is only an internal corrosion allowance of 1 millimeter. Well, there is no weld overlay, no cladding, and the class, by the way, the class, it was written maybe at the beginning, but the class, according to the table contained in part 5, is class 3B. Then, okay, we close this and we start looking at the various elements of this, the various components of this vessel. Let's start with the upper end. The upper end is an elliptical end. The material is carbon steel P355H EN 10028-2. There is an under tolerance of 1.4 millimeter, which is due to the forming process. The thickness is 14 millimeter. The inside diameter is 1100. the head ratio is 2 to 1, so this is a classical elliptical end. Under general, there is what is interesting here is the external diameter multiplier to calculate the head blank diameter before forming. This is important for the calculation of the elongation. Other things, well, group 3b, we have already, as I explained, the entire vessel belongs to the group 3b. Let's give a look to the preliminary report. The minimum required thickness for internal pressure is 9.6. It's clear that the reason for which a greater thickness, 14 mm, has been used is because we have to provide adequate reinforcement for the nozzles that are at the top. There is a yellow warning, or better, there are two yellow warnings. Joint coefficient is greater than maximum value. Okay, because we have used the 1 for the current testing group. Please check in case of a governing weld. So in case there is a transverse weld, this has to be calculated with 0.85. But since the end is made of one piece only, this note is not applicable in our case. The other note says exactly that since the elongation is greater than 5%, a heat treatment is needed. In fact, the elongation is 23.22%. Okay, we close this. And before closing this, well, better that we give a look also to another problem, the problem of fatigue, because this is the most important thing. All but welds do not check, of course, because there are no governing weld. This is made of one piece only. Knuckle region weld class, okay, this is important. Let's give a look to this table of the standard. What is applicable here, in the knuckle region, is the weld with the first shell. So this is a weld between two different thicknesses. Therefore, for testing group 3, the class is 63. In fact, we have written class 63. Condition of 17542 are met. What are these conditions? These are the conditions for the calculation of a number of cycles, of a minimum number of cycles for fatigue greater than 500. Well, this is not important in our case. It could be important if the purpose of this calculation was to see if the fatigue is applicable, if a calculation for fatigue is applicable or not. But we have started exactly from the idea that we must make this kind of calculation. Okay, well, then we go to the cylindrical part. The cylindrical part is also made of P355GH. The under tolerance method is absolute value is 0.3 millimeter, which is the normal tolerance for this kind of material. This is the length, this is the thickness, 10 millimeter, this is the diameter. Well, of course, we must give a look to the preliminary report. The preliminary report tells us that the minimum thickness for the internal pressure is 9.2 millimeter, so 10 is the correct thickness. For fatigue, we have to see longitudinal butt weld, general case with combined imperfections. The problem of any weld is the fact that there are imperfections. In the case of a longitudinal weld of a cylinder, the imperfections are of three different types: the offset, the overlay, the ovality, and the peaking. The offset is given by this table, offset of middle lines for longitudinal welds in cylinders. The cylinder is between 4 and 10 because it's 10, so the maximum we have decided to give these values the maximum allowable values according to the standard. We have 1 millimeter. The ovality, we close this and we look at the ovality. The ovality, the out of roundness, shall be calculated in accordance with the following. It shall not exceed the following values: 1.5% if the ratio thickness over diameter is smaller than 0.01. Otherwise, it's 1%. In our case, the diameter was 1200, the thickness is 10. It is certainly smaller than 0.01. Other problem is the peaking. What is the peaking? The peaking is the distance between the top part of the weld and the ideal circle. So any weld, any longitudinal weld will cause a small distortion of the edges of the adjoining plates. This distance is in the maximum allowable peaking is for thicknesses between greater than 9 millimeter, the lesser of the thickness divided by 3 or 10. Thickness divided by 3 is 3.33. So we have used the maximum possible defects. Then we have to look at the circumferential butt weld. General case, combined offset and unequal thicknesses, because of course it is connected to other components with different thicknesses. So what it is applicable is the detail, the same detail that we have already seen for the end class 63. Offset circumferential. In the case of circumferential weld, the offset, allowable offset, is different. For thicknesses smaller than 30 millimeter, it's 1/10 of the thickness plus 1. 1/10 of the thickness is 1 plus 1 is 2. There are no circumferential joker joints. Okay, we close this and we go to the next component. Next component is a flange. A flange, well, you have all the data. This made also a carbon steel material. Of course, the carbon steel material is the one which is suitable for forgings. Calculation is made according to the clause 11 of EN 13445-3. These are all the dimensions. These are the bolts and everything. Let's go directly to see the fatigue, the problem of fatigue. Welding neck junction to shell, weld class. This is a circumferential weld. Class, the detail is W71A. We are in this condition. Class 63 because the testing group is 3. Then unwelded hub to plate junction radius is this radius, the radius between the plate and the hub. We suppose that the junction is 13 millimeter. Of course, in this case, what it is important is to check what is the eta value. You have already seen in the lesson what is the eta value. Okay, well, we don't lose time for this flange because it's exactly equal to the other one. The lower shell is already a thickness, has a greater thickness, in fact. It's a thickness of 12 millimeter because this shell has the problem of the reinforcement with the connection to the cone. When we go to the fatigue, there is some modification in respect of the other shell. offset longitudinally is 1.2. The ovality is this time is 1 because this ratio has been exceeded. So we are now in this condition, thickness over diameter greater than 0.01. Offset circumferential is 2.2. Okay, because we have, if you remember, we have this table, so the circumferential offset, thickness divided by 10 plus 1, so 1.2 plus 1, it's 2.2. And then we accept this, we go to the cone. The cone has a thickness of 12 millimeter, like the adjoining shell. Preliminary report says that it is adequately calculated because the minimum thickness is 1159. For fatigue, we see that the situation is the same as the adjoining shell, more or less, because the thickness is the same. There is a yellow warning also in this case. The yellow warning is concerning the elongation, which is greater than 5%. This cone must be subject to a heat treatment too. Okay. Well, we don't lose time to look at the small parts, but maybe if we look at this part, this is important because it's a nozzle which has been welded exactly in the knuckle of the upper end. We have to clarify what is the problem of fatigue for this nozzle. Of course, there is no problem of calculation, longitudinal check, transfer check. You know that in the case of nozzles welded to the knuckle portion of an ellipsoidal or toruspherical end, the reinforcement calculation simply consists in increasing the end thickness, which has been already made, because if you remember, the minimum thickness was lower than 10, but we have used a 14 millimeter. In the case of fatigue for this nozzle, there is no longitudinal butt weld, so do not check. Circumferential butt weld with equal thicknesses and with offset. Circumferential weld class, detail W1.6. Let's look at this detail. 1.6. Well, circumferential seams only, minimum throw to equal to shell thickness. The weld root pass inspected, so there is no supporting plate, but there is a weld root pass inspected to ensure full fusion and a single pass weld. So the class is lower. In this case, we have a class 40. Other things, there is a warning too. Since nozzle is outside the limit, the head's calculation will take this nozzle into account when calculated minimum required knuckle thickness as defined in clause 7.7. Okay. Now we can give a look to the item report. Everything is okay except for some yellow warnings that we have already seen. Then we'll look at the report. Okay, now we zoom it a little bit in order to see it better. You see there is a table of content, there is an item property summary, but let's look at once what is interesting. Fatigue assessment summary. Fatigue assessment summary, here we have component by component, the allowable number of cycles, and we see that the limit is given by 6,773 is limited in load condition. There is only one load condition. The nozzle N3, opening in the shell, nozzle to two-wall weld, so it's not in the shell, it's in the upper end. But this is exactly what we have seen, the nozzle N3, 6,773. The conclusion is that certainly the required number of cycles, 1200, is acceptable. But let's look a little bit better at this table. Of course, we should expect that since the nozzle is welded in a critical region of the end, so the knuckle region, certainly there is a greater stress concentration than in other locations. But what is a little bit surprising is that also a longitudinal butt weld, the longitudinal butt weld in the conical shell, seems to have some problems. 7,000 cycles, almost the same number of cycles of this clear stress concentration. Why there is also a stress concentration in this weld? The reason is that we have considered all the maximum possible defects of this weld. Let's come back at this is the cone. So we close now the report and we look again the cone. And we look for fatigue, the longitudinal butt weld in the cone. We have used the maximum possible defects of this weld. Defects are three types: maximum offset, maximum ovality, maximum pitching. Suppose that we take 50% of these defects. Say instead we open the locker, and now instead of for 1.2 we write 0.6. Instead of 1 we write 0.5. Instead of pitching we write 50% of the maximum pitching. Okay, we confirm. We look at the item report again. Report. And then we go to the fatigue assessment summary. We make it a little bit bigger. And we look now at the cone, conical shell, longitudinal butt weld. Instead of having 7,000 and something, we have 25,000 and something. Well, that is a problem. So, of course, if we make a design, we must take into account the capacity, the maximum possible capacity of our shop. The maximum possible capacity of our shop, if we do not make any special agreement with the shop, is in any case the maximum possible defects permitted by the standard. Of course, you might impose to your shop defects smaller than the maximum possible defects of the standard, but this will become a difficult situation of the relationships between the technical department and the shop. In many cases, it's a normal situation of all the manufacturers, the pressure vessel manufacturers. With this, I have finished, and I thank you very much for your attention.